Right, now the collision theory is a new way of looking at, please explain why. Please explain why. We don't like those questions, please explain why. But the collision theory is about particles must have sufficient kinetic energy and they must have the correct orientation and they must collide in order to cause a chemical change. And a chemical change means old bonds are broken, new bonds are formed. Yes, Sangi.
So, ma'am, particles for a reaction, for a chemical reaction to take place, the particles have to reach the collision theory. Technically, like particles need to have kinetic energy, like
Enough kinetic energy.
and also a correct orientation.
Yes.
Ma'am, when we talk about correct orientation, what does that mean?
Okay, I'll explain just now. And they must collide to form new bonds. So these are the three. They must have sufficient kinetic energy, they must have the correct orientation, and they must collide for a chemical reaction to take place. Let's look at oxygen and hydrogen. So we've got oxygen and we've got hydrogen in a container. These molecules will not react unless they have enough kinetic energy. Their collisions must be strong enough. Okay? They must have enough energy when they collide. So when they are moving towards, when these molecules are moving towards each other, oops, sorry for my poor board work here. if they move towards each other and they just bump into each other, and their kinetic energy is less than the activation energy, no reaction will take place. There will be no reaction. You understand? So that EA, yeah. If the kinetic energy is less than the activation energy, they can bump into each other, but it's like you when you pass other people where there's lots of people. There won't be any reaction if you rub shoulders as you pass. No problem there. No reaction. But if somebody comes and really move fast and you collide vigorously, if somebody does that to you, you're going to punch him back. It's just a natural reaction. You will punch back. You will think this person is deliberate. Okay? And there will now be a reaction. But the reaction will not work if these molecules don't attack one another in the right orientation. So what must happen is these molecules must collide strong enough, and they must collide with the right orientation. If they collide like this molecule is going to collide with that molecule. These bonds will be broken. So you have enough energy and they've got the correct orientation. Then the oxygen will break up, and each oxygen can form two bonds. Okay? And the hydrogen will break up. Are you with me? When they collide with the right orientation, they collide in such a way that the bonds will break.
Is the orientation the position of the molecule?
Yes.
So now,
if they collide like this, they're not attacking the bonds. They're just two molecules that will, the oxygen hits the hydrogen, but there's no attacking of the bonds.
So then do the bonds have to be like open to one
Yes, so that the old bonds need to be broken. So they, like you said, open bonds on the atoms. Now they can form bonds. This oxygen can form a bond with a hydrogen, and that oxygen can form a bond with a hydrogen. Now obviously I don't have enough hydrogens here. I'll need 2 hydrogen molecules for every oxygen molecule. That's where the idea of a balanced chemical equation comes in. So if you want oxygen to react with hydrogen, there must be 2 hydrogens so that 2 water molecules can form. Yeah. But it's important to understand that there must be sufficient energy and they must collide with the correct orientation. Obviously we can't determine the orientation. Usually when there is enough energy, they will sort their orientation out automatically. They must just collide in order to form new bonds. Are you happy? So orientation is needed and collisions.
So now they have enough kinetic energy when it's over, above the activation energy.
Equal to and above the activation energy, yes.
So in order for them to react with each other, besides having enough energy,
Their bonds need to collide.
The molecules need to collide. The particles need to collide. Right, now we need to go to the please explain why of those factors. So we must use the collision theory to explain why an increase in concentration will increase the rate of a reaction. So use collision theory. So why would increasing the concentration increase the rate of the reaction? If we look at collision theory to explain it, what is it that is more if you have a higher concentration or a higher pressure if you have gases? What is it that is more? The not volume. Why is the rate more? We need to get to the reason for the rate being more. If you increase the concentration, compare the dilute hydrochloric acid we had yesterday to the concentrated hydrochloric acid. The amount, yes. The moles of the reactant is more than, so you have more particles in that concentrated solution. So what will more particles do? They will collide more often. More particles will collide more often. So the chances of an effective collision will be greater. And that's why the rate of the reaction is bigger. So use collision theory, a higher concentration of a reactant will have more particles. You can say molecules or atoms or ions or whatever. I'm just using the general term for those particles, molecules, whatever. More particles present and more particles will then collide more. So the chances of effective collisions are greater. If you have more effective collisions, the rate of the reaction is increased.
Sorry, ma'am, is the catalyst also part of the factors?
Yes. So use the collision theory to explain why, if there's a greater state of division, the reaction will be faster. That is the situation. So a greater state of division will do what? So it will free up more particles that would collide more often. So the chances of effective collisions will be higher. So a greater state of division will cause, or will, can I say will free up, will allow more particles to collide in the same time. Can I say it that way? More particles. If you've got the clump of calcium carbonate, only the particles on the outside of that clump of calcium carbonate could be attacked, could have effective collisions with the acid. But now, if you've got powder, you have more particles that can be attacked by the hydrochloric acid at the same time. So there is a greater chance of effective collisions, the rate of reaction increases.
Right now, are we explaining in terms of collision?
Yes, yes. So a greater state of division will allow more particles to collide in the same time. So there is a chance of effective collisions are greater, and therefore you have a higher rate of reaction. Why at the same time? You see, here you'll just have a few particles that can be attacked by the acid at the same time. Because the calcium carbonate was in the acid, so it's attacked by the acid from all directions. If you free up those particles of calcium carbonate by changing it into a powder, the same acid, but more acid molecules can reach the calcium carbonate particles now in the same time. So the reaction will be faster. In the unit second, there will be more effective collisions. Understood?
Yes,
So this one is, you need to add the temperature effect. Increasing. So increasing the temperature will increase the kinetic energy of the particles. They will move faster and collide more often greater chance of effective collisions. The rate increases. You remember the Maxwell-Boltzmann curve?
Yes.
Okay. How will the curve change if the temperature of the reagents are increased? Okay. This whole curve will shift towards the right. So I'll draw it out for you so that you can see what I mean. More particles will now get energy that is greater than the kinetic energy. So this is what happens. This is the curve for a higher temperature. The activation energy is there, and these particles now shift to a higher energy state. So more, much more particles will have energy higher than the activation energy. So the reaction will be much faster at higher temperature.
So this goes under temperature.
Pardon?
This graph goes under temperature.
Yes.
So the black graph is the one that has a higher temperature.
Yes. The
and
blue
the
one,
blue one is the lower
yeah,
temperature.
lower temperature. I haven't done this graph under concentration. If you increase the concentration of a reagent, you add more particles to the reaction chamber. So the blue is the original curve at the lower concentration, and the black one is higher concentration. And with higher concentration, you have more molecules that's got energy higher than the activation energy. I was just thinking about this graph, and I saw it for the first time in the past year. It wasn't in your textbook, so I thought afterwards I need to add it to this video, just for in case it comes your way. You never know what will come your way. So number 4 is adding a catalyst. So a catalyst reduces the activation energy. So use the collision theory to explain how it happens. So a catalyst reduces the activation energy and that causes more particles will have energy enough to collide effectively. And that leads to an increase in the rate. Yes.
So now, with adding a catalyst, like in terms of the Boltzmann curve, it moves the EA back.
Yeah. So adding a catalyst will move the EA back. So the energy, the general energy of the particles will still be the same. That's the original EA. And if you add the catalyst, you decrease the EA. And now, those same particles more of them will now have enough energy to react, to collide effectively. An effective collision is a collision where the rate is increased. Can you remember what the effect was on the energy profiles? Those graphs.
And also
the maximum height of the graph like these. So.
Yes. So the catalyst did that. Less energy is needed to break all the old bonds if you add a catalyst.